To make a blue dot appear on a map, your device must communicate with a swarm of machines hurtling through the frozen vacuum of space at nearly 14,000 kilometers per hour. This process relies on the precise heartbeat of decaying atoms and a massive cosmic infrastructure. For millennia, finding a location required external reference points. Sailors relied on the stars, and early radio towers provided some relief, but these terrestrial networks were limited by the curvature of the Earth, atmospheric interference, and heavy weather. A solution arrived by accident in October 1957, when the Soviet Union placed Sputnik 1 into orbit. The silver sphere emitted a steady radio broadcast, a series of simple beeps at 20 megahertz. Listening to that broadcast, two physicists at Johns Hopkins University noticed a pattern. The frequency of the beep shifted higher as the satellite approached and lower as it flew away. By measuring this Doppler effect, they realized they could calculate the exact speed and trajectory of the satellite from a single ground station. The engineering logic proved that if a known location on the ground could track a satellite, the mathematics could be reversed. A known satellite in space could be used to pinpoint an unknown location on the ground. At the height of the Cold War, the United States Navy required a way for its nuclear submarines to update their navigation systems without surfacing for long periods to track the stars. This led to Transit, the world's first satellite navigation system. However, because the satellites were in low orbits and few in number, a submarine might wait several hours for a signal, and calculating the location required massive computers and a significant amount of time to process. To solve these inefficiencies, the Department of Defense merged several disparate tracking projects in 1973 into a single, cohesive program, the Global Positioning System. Modern global logistics and navigation required a network that functioned instantaneously and continuously. The early wait and calculate systems could not provide the flawless accuracy required for a world increasingly dependent on precise timing. This is the structure built in the sky. The space segment consists of a constellation of satellites arranged in medium Earth orbit. By placing the satellites in 6 distinct orbital planes at an altitude of over 20,000 kilometers, the system guarantees any point on Earth has a direct line of sight to at least 4 satellites at any moment. These satellites act as orbiting radio stations, continuously broadcasting only 2 pieces of information: their exact location in space and the exact time the signal was transmitted. By measuring the time it took the signal to travel at the speed of light, a receiver calculates its distance from the satellite, a measurement known as a pseudo-range. If a device knows its distance from a satellite, it is located somewhere on the surface of an imaginary sphere centered on that satellite. 2 intersecting spheres create a 2-dimensional ring of possible locations. Adding a 3rd sphere narrows the possibilities down to just 2 distinct points, one deep in space and one on the surface of the Earth. Because radio waves travel at the speed of light, timing must be absolute. A timing offset of just 1 millisecond results in a 300-kilometer positioning error. Since smartphones rely on inexpensive quartz crystal oscillators rather than atomic clocks, the spheres of distance they calculate are always slightly too large or too small, failing to intersect at a single point. A 4th satellite signal provides the additional variable needed to solve for time. The receiver's processor continuously adjusts its internal clock until the spheres intersect at a precise location. This synchronization allows a consumer smartphone to function with the temporal precision of an atomic clock. The 4th signal provides the altitude and timing correction required for 3-dimensional positioning. Even with atomic clocks in space, engineers faced a hurdle involving the nature of time itself. The physical principles of relativity dictate that time does not flow uniformly across the universe. 2 opposing forces are at play. Special relativity dictates that high orbital velocity slows the clock by 7 microseconds per day. General relativity dictates that weaker gravity causes the clock to speed up by 45 microseconds per day. The net result is a relativistic drift of 38 microseconds per day. Without continuous correction, this discrepancy would cause a positioning error of 10 kilometers every 24 hours. To correct this, engineers intentionally detune the atomic clocks on the ground. Set to run slightly slow, the clocks speed up to the required frequency once they reach orbit and the warping effects of relativity take hold. Every time you open a digital map, your device actively relies on Einstein's theories to function. It stands as the most prominent daily application of relativistic physics in the modern world. For decades, the civilian signal was intentionally degraded for military security. On May 1, 2000, an executive order deactivated this feature, instantly upgrading civilian accuracy from 100 meters to 5 meters and enabling the modern trillion-dollar logistics and mobile industry. Yet relying entirely on a single foreign military system carries immense danger. During the 1999 Kargil War, the United States denied the Indian military access to high-precision navigation data, highlighting the vulnerability of relying on another nation's infrastructure during a conflict. In response, powers around the globe began building sovereign constellations. India developed the NAVIC system, placing its own satellites into orbit to guarantee independent positioning and timing data. As reliance on satellite navigation grows, so does the threat of spoofing. Because the radio signals from space are extremely weak, malicious actors can broadcast counterfeit data to hijack a receiver's tracking loops, feeding it a false location without triggering cockpit warning alarms. The system's inherent radio transparency enabled global commercial adoption, but that same weakness now functions as a tactical vulnerability in modern electronic gray warfare. The United States Space Force is currently deploying a modernized fleet of Block 3 satellites to combat these vulnerabilities. These spacecraft feature enhanced signal strength and advanced anti-jamming capabilities. This new architecture includes the M code, a heavily encrypted military signal. It utilizes directional spot beams to focus intense bursts of secure navigation data down to specific areas, physically overpowering regional jamming blankets on the ground. Future civilian safety will depend on sensor fusion. Next-generation receivers will cross-reference satellite signals with internal barometers and inertial measurement systems to mathematically prove a signal's authenticity. The global positioning system remains a continuous dialogue between the vacuum of space and the device in your pocket. By marrying orbital geometry and the constant correction of relativity, it quietly defends humanity's ability to answer our oldest question: where am I?